Okay, I think that we can slowly start and discuss some important fundamentals. So the main idea of this course is just to uh, make a fresh or contemporary impact on the very basic of logistics, quantitative logistics especially. There are many properties of this topic, but I suggested to uh, add some interesting features to this that is very new, and I hope it will be interesting and useful for you. I would like just provide right now some basic ideas of this course, just to give you the entire picture. I will start from the very example. So it's a Bryce paradox. Maybe you know it already. So we, okay, sorry. Um, okay. So it states that if we have, for example, A point and we have B, yeah, when we talk about logistics, of course, there are many problems and many tasks that we should solve when we when we want to succeed in this. But sometimes we will focus on especially on routing and networking and other things, because it's something very special about logistics. But we also can mention, or we can use these methods not for routing, but for some other thing like, um, I don't know, arrangement and so on. Okay, so about routing now. We have point A, point B, point C, point D, and we have 4 rows. The time from C, yeah, from C to B is a constant, it's 25 minutes, and here 25 minutes. And from A to C and from D to B, it's a special formula. It's just a number of cars divided by 1000 here. But a number of cars who want to get from A to C, from D to B. And we have cars. Well, no. So the total amount is just, wait a minute. It should be, yeah, 40. Yeah, cars. And there is a traffic problem. So how many, how much time it takes to get from A to B for this 4,000 cars? Well, okay, it's a very symmetric thing. So we can imagine that NAC equals 2,000, and we have, well, sorry, 10. Okay, and we have 1,000, and we add 25, and we have 45 minutes for each car. It's okay. But then we want to construct a special road, additional road from C to D. Very short road. We can expect that this time will be smaller for all these cars to get from A to B. But unfortunately, it's not. So it was found many years ago that the situation when every car goes from A to C, then from C to D, and from D to B, it takes 40 minutes here, okay, 0 here, 40 here, so total amount. And it is equilibrium. So no car wants to change this. Well, sorry, wait a minute. 20. I'm not sure about figures, but I will give you an idea and then I will check twice this one. So the idea that they don't, well, they no car want to change to this point. Go to here because it's not profitable to this car. I will show you the correct thing. Oh, sorry. Later. So the main idea of this Bryce paradox that equilibrium is something that we should take into account when we talk about traffic jams, about traffic, about logistics. So when we want to make a routing in our system, we want to create just new streets. Another thing, we have to think how people will use it. Another example for this is the situation with the chicken game. So, yeah, okay, sorry. I have a conversation here. Wait a minute. I will check your questions. Okay, from C to D is just our assumption. We can focus on the profitability and the profit of um, road from A to B through C and D. And if you want to focus on this, we would like to make the time from C to D as small as we can. So it could be not 0, but 1 minute or 2 minutes. It should be very small. Okay. The chicken game. So the idea is that we have also routing. We have point A, we have point B, and we have options. Now we have directed ways here. And there is a car who wants to get from A to B, and there is a car who wants to get from B to A. One car here and one car here. And there are several ways. So it can be A, C, B, or it could be directly from A to B. The problem is that this road is there is a bottleneck, and only one, well, just like a road or tunnel. So only one car can go through this road in any direction, but they cannot go both this car um, on through this road. There will be a crash of this. So there is a choice for each car. They go to the this direction or to the direct way. We can show it like this. I will tell more about a payoff function, but later. So okay, the first version directly, and A to C, and then to B, and here from B to A directly, or B to D to A, and we have 4 variants for this. So here. So crash for both. If they go through C and D, It's a long trip for both of them. And the Nash equilibrium is just here and here. But the problem is how to choose it, because no one wants to be in a bad equilibrium for him. So, well, so the equilibrium is when a car goes from A to B or from B to A using the long way, and another car use the direct way. It's the Nash equilibrium. They cannot use both long way. It's not a Nash equilibrium. I will tell about a formal description later, but equilibrium is just it's just an idea how we can predict what will happen in this system. And we see that there are two equilibriums, but it's a problem how to choose which one. It's a kind of coordination problem here. So it means that we should and use some kind of reasoning of another player, another actor. Okay, the second one. Okay, but what about uncertainty? We had no uncertainty in the first example. We had no uncertainty in the second example. What about the third situation when we have uncertainty? Let's imagine that we have a routing system. We can enumerate it, but we just put 2 points here. And we have two cars, A and B, and several roads. But maybe not all of the roads are known for these cars, for both cars. For example, from the, okay, I'll enumerate it here. Okay, and maybe this street from A to from 1 to 2 is known only for car A. This road is known for car A and B. This one only for B. This one only for B, for A, for B, for A, and for B. And they are trying to solve like a traveling salesman problem or any other routing problem, and they can compete on this routing system. But as you can see, the car A has to think, or he can get information from the behavior of another car, because because for example, from 2 to 4 street is unknown to A. They don't know that there is a street here. Well, of course, it is difficult to imagine that there is no information about a street. Okay, but here is some kind of abstract thing about like traffic jams or repairing. So when the street is out of service, so we have a map of our city, and we know all streets, but we don't know about which one is ready for routing and which one is out of service. So this is the main idea of this. Of course, they can get some information from Google or from GPS and other navigators. There are such services, but in some cases they're not. They don't provide correct information, or especially when we have not a capital of the country, but some small villages for this. Okay. Another, so we have some kind of uncertainty. Another classical problem that we can have. So let's imagine the classical a traveling salesman problem. It's very important in our course, so I will pay attention to this. So the main idea is that we have several points. Sorry, like 1, 2, 3. Oh, sorry, 3, 4, 5. There is a network here. For example, the kind of a map. So you can imagine that it's just a cost function. Where is A, G? Oh, it's just a cost of time or money that we should pay to get from the point I to J, from I to J. Here. For example, here it's okay. And the problem is that we want to visit every city here. So we want to get, for example, from 1 to 2 to 4, then to 3, then to 5, then to 1. It is known that it is a very difficult problem. So it's, well, sorry, NP hard. But there are some heuristics like branch and bounds. Algorithm to solve it. Here we're talking about only one car. Okay, but what can happen wrong in the wrong way? Let's imagine that we don't have a certain knowledge. But we don't know these expenses here. For example, it can be out of service with the probability J, with the probability Pij. We don't know. So if this specific road is available or not, we can understand it when we try to go from this point to another one. For example, when we get to point 1 and we want to get to point 2, there is dice, and there is a probability that this road will be out of service. We cannot predict it. We know only a probability distribution. Well, just we can pay this cost, or there is infinitely large course we can get from this point to another point. And what should we do in this case? How can we transform our algorithm and methods for traveling salesman problem, for example, by branch and bounded algorithm, to get a solution? For example, we want the maximum expected payoff or something other thing. It's some kind of problem here because we have to talk about probabilities. Another thing is when we have interval uncertainty. So when we don't have a probability, but we have some kind of bounds here. So we know that there is a lower bound and there is upper bound to get from point I to point J. We don't know probabilities or distribution. We know just bounds. What will change? Can we modify our algorithm to get solution for this case? Because in real situation, uh, sometimes we don't know the exact time, so it's just expected time to get from one point to another point. Another version of two players logistics is that it's a competing salesman. So each of them, from one of them starts from point A and another one starts from point B. They have the same problem. They want to visit every city in the here, but we also can give them a special payoff function depending on the priority. For example, we can say that the salesman who gets to the town first gets more payoff. For example, there is a payoff here for A, agent A, payoff maximum if this agent can get to this town before back the another agent can get there, or he can get a payoff if another agent gets to this point before agent A. What will change in this case? So when we want to solve a a traveling salesperson solution, now we should check, or we should predict how another player will act, because we have to, for example, we understand that this road is very short, this one is very long road, short. And maybe for A, we know that this is a very large thing. For example, I don't know, maybe that's 100, but this one just 1. And in this case, well, in the end we have another thing here, just not well, and we have, for example, yeah, and 5. And here A wants to get to point 1 here to get this payoff. But since, this road is longer, so maybe he don't want to go there. Maybe he wants to go to get to the second point. Well, for example, if this one, sorry. Yeah, to point 2 to get some profit here, because he understands that B will get to the point 1 before he can get there. But it depends of payoffs of B and so on. So it's some kind of rather difficult problem, even if we have very simple network. Even with two nodes, we have to write down game theoretical form and check equilibrium and optimal things. Another thing, maybe the last variant for today, is the situation when we have several options for networks. For example, I want to get to visit from A to B, to get from A to B. Yeah, to B. But I don't know which one, this one or this one. C, D, C is the correct description of this network. It's something similar to the previous task when we had several threads out of servers. So we can use description, like in modal logic or in epistemic models. We can say that agent, before he acts, he cannot recognize which picture is the correct description of the situation, this one or this one. And he had to find an algorithm that will help him to find the optimal solution. So he has to predict or try to predict all possible situations. Okay. Yeah, and I have told that this is the last one, but maybe I should add one more. When we talk about logistics and we talk about agents and so on, sometimes it's very important. It's maybe not for computer science, but more for business. But it's important. It is very important for agents modeling. So we have some kind of business process. What kind of process? So there is an agent who wants to get some goods from one point to another. So it's products here. He has a product and he wants to get it to the customer. Or maybe they have to get order, then product arrangement, product to customer, and then go to customer, and so on. And every time we have a real situation, applied situation, we have such a maybe very simple a problem or very simple business process, and then we have some probabilities here, and we also have sometimes to motivate a traveling salesperson or another guy to make this work done. For example, you can imagine that our profit function is just f, which is the h, and and x is efforts of an agent, employer. So it's just a number. So the larger efforts, the greater efforts, the more profit we have. And we have some salary, depending on x, and a profit function, utility function for the agent. So it's his salary minus his costs. And it could be a problem. In this case, it is solved, but there are many modifications. When we want to define, if we know H and we know C, what sigma should we define? It's like a contract for agent, for this employer, to maximize our F. It's a function. And we know that agent choose his efforts based on the solving optimization problem for his utility function. Okay. Oh, I have listed all slides. There are several problems for this. Okay. If you have any question, you can ask me. If you want, you can ask directly using a microphone, or maybe write down in the chat a discussion. I will try to answer. Okay, we have several problems for this basic. What we want to to get from this. So we want to have some algorithm, and we want to have a method how to solve all these problems if we have it. It's very important that we will try to make our problems very applied. We don't want to solve just abstract mathematical problems. We would like to solve some problems that have a very clear interpretation for some cases, and we want to involve agents and reasoning and probabilities and other things that will help us to adapt a solution that we already know to this situation. It's not a chaotic in strict definition, but it's something that can go wrong, and we want to predict it. And another thing, it's quantitative. It's very important because we are not in a high business. Well, we are not at high school of business, for example, or MBA. We pay attention not only just for methods of thinking, of motivation, how we should check our priorities and so on. No, we will focus on mathematical, computer science, programming, and other things. So we want to have solution in mathematical form. Maybe in some cases we want to have a software to solve something, or we want to have a solution like equilibrium. So we want to be very connected to mathematical models. We want to use maybe probability or epistemic model theory, logic, game theory problems, and we want to use software. So all our algorithms should be very useful, okay, to solve uh, applied problems. Wait a minute. I will check chat. Sorry. Cannot see messages. Wait a minute. Please. Okay. Okay. Yeah. Okay. I just saw. Uh, I just seen the question. So yeah, there are several books. I would like to start from the books which are core of this course, but we will update it to get to put into this program more about logic, game theory, multi-agent thing. It's some kind of not secret, but additional additional parts which are not described right now on the site. So we will change a bit. But there are 3 books. I will show you. Wait a minute. Okay. Here. Unfortunately, I'm not sure why it does. Okay, I see. Yeah. So I will just use Chrome here. Okay. The first book which is recommended to to read, but well, it's very difficult and complicated book. So I'm not sure that it will be very easy to read it right now. We will have some theorems from these books. We will have some reference, but don't think that you have to read all these book entirely. No. So just several parts of this. So it's data correcting approaches in combinatorial optimization, the first one. The second one is cell formation in industrial engineering. And the third one, networks in action. We will discuss today this book, Networks in Action. It's well written and it's rather simple to understand some basic problems for this. When we will talk about games and we will talk about reasoning and other things, I will provide more references, more good books about this. There are several of them, uh, but it will be a bit later, just not to mix. Okay. And the question about tests and homeworks and so on, it's a very important thing, and I would like provide you with this information. Wait a minute. Yeah, here. Uh, as you can see in the left middle of the screen, we have a final exam. Well, comprehensive. Yeah, just final exam where you will have an opportunity to answer the question and discuss some basic points. We will have homework and assignments. I'm not sure if we have it in the third or in the fourth model, but I will tell you in advance when it will be time for doing this. So it's homework. It will be a short test, just maybe basic definitions or something very basic things. And I think it's one of the most interesting thing, uh, but it's not well paid here, unfortunately for me. But I think it's okay because we have exam, homework, tests, a lot of this. It's some kind of team reports. I think that it's very similar to homework or assignments. So you will choose uh, a problem and you will try to solve it using software or by mathematic modeling. As I know, we have the third and fourth model, and we need this rating on the fourth. So we don't need this at this point. So we have time to prepare. Okay, so there is no scoring or rating for just visiting or attending these lectures. Um, we don't have this in this course. We have exam, we have homework, and some other thing. Um, I don't think that homework will be very hard, but it depends. We will discuss maybe later. I- Is it clear right now about rating and other thing? I think it's rather clear. So in general, there are three ideas. So you have to know something, you have to solve problems, and you have to solve, well, work and to create a presentation. We can say some kind of research. So solve problems, typical problems, maybe research, and no terms, no basic definitions, no definition, or ideas. This one. Well, the very important thing that I have to tell that it, I would like to adjust the complexity of this course to a level because I want this course to be useful for you. So it can be very easy to understand and maybe it's obvious. In this case, it won't be very useful for you, of course, because you just spend time for nothing. Uh, but maybe it might be very complicated, difficult to understand with no clear applications and other thing. And it's also no usefulness in this situation. So I would like to make it more, mm, more close to your needs. So if you have any ideas or remarks, please let me know. For example, you understand that you have a problem in your mind that is very well, a problem in your mind. I mean, you have created or invented a problem that you want to solve uh, about multi-agent, about logistics, and you can just share with me, and I can give you as a project or maybe homework based on this problem, such that you will have methods and algorithm for solving uh, your problem. Well, the problem that is very important for you in this case. Because I think it is possible because we only have 4 students here, maybe 5 or 7, but just not so a large number, and we can discuss many things in a direct way. Okay. What we will discuss? So here, okay, wait a minute. I will check if I have answered everything. Yeah, repost. Okay. Can you okay. The second book. Okay. Yeah, I will show you. Okay, wait a minute. The second book. This one. It's self-formation in industrial engineering. It's optimization, but it's more. All these books are more about classical fundamental algorithm for optimization. The main challenge for us, for you as students, and for me as a lecturer, to adopt some methods from these books to uncertainty, multi-agent, and other things. Okay, so for us, it's just a very basic thing from where we start. Okay, okay, okay. Check discussion again. If we have any new, okay. Okay, yeah, I'm going to share these recordings with you to provide you with this information. I think it's okay. It will be very convenient for you to watch these lectures and watch it again maybe, and to get some clarification, some cases. Okay, nice. Okay, so let's check what kind of fundamental things we need. No need. So the first one is understanding of shortest path algorithm. I prefer wave algorithm. Maybe you know it. I will tell about this. It's the way how to find shortest path from one point to another point. Another thing is a traveling salesman. I think that it's not a problem to consider a greedy algorithm. Well, sometimes when I say words that you don't know, for example, I don't know, maybe greedy algorithm or other things, please don't be afraid. It's just maybe some kind of uh, description of the content of the course. So you can ask what this term means, what this term means. I will explain step by step. But I think that the first lecture is just some kind of introduction for us, just to, and for me as lecture, it's very important to show you the key points of this course, and to make it not boring but interesting for you. So I'd like to show the problems that you can try to solve right now. Maybe you know the solution for all of these problems. And you say, oh, okay, this one I know it will be maybe boring. This one I don't know. This one is very interesting. So and then you will pay attention to this problem especially. So the first idea is some kind of showroom of problems here. But later, today maybe, I will start from uh, step by step from the very beginning and so on. So maybe it will be a bit boring sometimes if you don't know, if you already know game theory or logic. So if not, it can be very interesting. Okay, so shortest path, a traveling salesman problem, uh, and some heuristic here, assignment and shadowing here we use. Okay, wait a minute. Yes. And we have several descriptions for branch and bound algorithms for symmetric, asymmetric. Maybe we can skip some topics here, because now in the age of internet, in informatics and a lot of knowledge, so maybe it is not so important to pay attention to every detail of this algorithm, because you can easily just read it in the internet. I think that the most important is just to discuss some challenges. Okay, data correcting approach here we have. Uh, Introduction to submodular function. The idea here is that we can sometimes solve a traveling salesman person problem or some other logistics problems for the special cases much faster than in common case. So if we have a functions of a special kind, so we can solve it, and we have special algorithm, and there is a book about this. But I don't think that we should focus on this too much. So we just check how we can adapt and use this algorithm, but maybe not dive into the proofs with all details and so on. Maybe if you want or we need it for some cases, we do this, but I would like to stay as simple as it is possible just to solve our problem. Okay, we have some theorems here, like this one. We also check a quadratic cost a partition problem here. One more theorem, a polynomials, simple multiplication, and so on. There are many theorems here, but maybe we skip some of them to keep our lecture very simple and clear. Okay, wait a minute. I don't know why I don't have an ability to read chat directly. I would check what's wrong. Okay. Report. Yeah. Okay. So I think I have answered all the question. So how much? Okay, we have a lot of time. Okay. Now I can start from the very beginning. Wait a minute. Ooh. First of all, I would think we will think. Well, I would like to classify what kind of problems we have. So we have logic or epistemic model. We have uncertainties. Oh, like probabilities. And we have agents, decisions, and so on. What do we need? So I think that we should start from agents, then go to uncertainty, or maybe logic and then uncertainty. Okay. When we talk about multi-agent system or logistic problem, when we have several agents or several customers who can act or can order something or something, we have several employers. Yeah. By the way, I would like to mention that there is a very interesting situation how to solve a logistic problem, multi-agent problem, when we just assign, or when we create virtual agents, we assign one agent to one customer and one agent to one salesman, and then we try to find the optimal routing or arrangement using genetic algorithm or some other numerical algorithm. I was told that one professor from the Samara from Russia, he applied this for taxi drivers in London, in United Kingdom. So it's very multi-agent approach. Unfortunately, there is very difficult to prove theorems there. So we have only software. Well, not we, but he has only software. We will try to stay as much as we can close to mathematics directly. Okay. So when we talk about why do we need a game theory here? And is it about just games like like Dota or Counter-Strike? No, we will talk about games in the sense of economics. Like Nobel Prize winners do, or for example, economists do. So we will talk about, usually we will talk about that we have agents or players or any other word for acting people or robots, for example, something who can act. It's usually it's a set, and we can have enumeration here, for example. Sometimes it's funny, but people they have, well, uncountable, uncountably many agents like an infinity. They do this to model situation with social networks or other things when we have about 1 million or 1 billion agents. Then we can try to use models with uncountably many agents, but usually we don't. Usually we have a finite set, and we will have a finite set here in our models. Then this agents has some strategies or sets of strategies. So for example, agent, the first agent, he has a set of strategies x1. It could be like left or right. He can choose if he go to the left or to the right. So we can just list here. Here we don't have a restriction on countability, so it can be easily x1, can be easily just real numbers in uncountably many values here. So it's strategies. So agents have an opportunity and have an ability to change something in the model. He can go to the customer, they can repair some road or the street, they can change routing and so on. So it's the second here. And the third, that is very important, is utility function, PIO function. utility payoff. It depends on the article and professor, but we can use utility or payoff or even other thing to describe the usefulness for this agent, the situation. So agent, the set of agents, they choose, each of them choose some actions or strategies from their sets, and then they have utilities. Utility is just a function such that for every combination of chosen strategies, it gives real number. The idea is just that it has some money from this state of nature. So people, agents, they act, they do something, and they have some final state of system, and he get a payoff from this final state. Very basic idea. Now this construction is normal, is so-called normal form game. When agents, they act independently, so they cannot cooperate with each other. So they do it simultaneously. So there is no ordering, no cooperative, and there is a perfect information about rules. So there is no uncertainty here. So it's a normal form game. The very important, well, the very famous situation is a prisoner's dilemma. There are a lot. There are many articles about this. So I just say that it's a game with two agents. They have just to cooperate or not to cooperate, two strategies, and they have payoff there. It is very interesting that well, later, okay. And then what do we have? We have here we need some kind of equilibrium. We have to understand how people choose their strategies from these sets. From here, what is the way? And there are several so-called equilibriums. Equilibrium, like Nash, dominated strategies, or like a result of rationalization, and other variants. So what is it? So Nobel Prize winners and other very famous professors, they just suggest, they have invented several ideas or algorithm, or maybe directions, how to predict the strategies of agents. What will they do? And it's very difficult because some people they say that we have a free will, or agents have free will, so they can choose whatever they want. So we cannot predict what people do because they are too complicated. People can make mistakes, they can do something wrong, unreasonable, they can be affected by their emotional state and so on. So there are people who say that it's very difficult to predict. And even well, it's not only in the Soviet Union, for example, or from some linguistics or maybe philosophy departments. Uh, for example, there is a school of economics in the Netherlands where they think that man can have free will. So we can just expect from him, but it's not obligatory for agents to follow this our rules. Okay, and I will just show you the very famous thing that will give you an idea of what kind of equilibrium we can handle. So it's Nash equilibrium. There are several versions of it, of description of this equilibrium. I prefer the following thing. We have agents here, and agent 1, he has a chosen strategy 1, agent 2, chosen strategy 2. They have more strategies, not just S2, but they have such 2 here, and so on. Okay, we have. And we want to check if this vector from the Cartesian product of all these sets is in equilibrium. Yeah, and they have payoffs. So the first one have payoff. This, and the second have, well, payoff or utility function. I will use utility function for some reason. And so on. Some functions. And we would like to check if this vector is equilibrium or not. The idea is that if we ask someone, for example, we think that maybe, well, I denote here, maybe this vector is an equilibrium. We ask all of them, choose it, and we go directly to every agent and privately suggest him to change his strategy. So it just, man, you have choose, for example, it's an agent I, your strategy, but you can change your strategy, but all other strategies will stay the same. So it's some kind of an additional step. And if this agent, every agent here, this one, this one, this one, he's completely satisfied and he don't want to change his strategy, then we say that this vector is a Nash equilibrium. Well, we can write it down in a formal term. So this vector is an equilibrium if for any I, we have that here is less. Yeah, if here is a formal definition. Yeah, for Nash equilibrium. So all such combination of actions which has the following property, they are all Nash equilibriums. Okay, it's very important that agents can cooperate. There are many articles and a lot of research about cooperative game theory. It's very interesting. There is a Shapley value, core value, and other things. But we would like to stay a bit out of this area, uh, uh, out of this domain, to keep things as simple as we have to. So it's a Nash equilibrium here. The problem with Nash equilibrium, I can show uh, at least two problems. Well, it's a very good thing, and there is a Nobel Prize for this. Nobel Prize. Well, it's not no Nobel Prize. It's just a Nobel. It's some kind of a Nobel Prize for economists. So it's the not Nobel Prize, but the prize. I don't know the correct spelling for this, but we usually use just Nobel Prize. But even Nobel Prize winners like Alman, he makes he don't know this. Well, he knows, but he use Nobel Prize winner sometimes as a description of this prize, but it's not the exact meaning. Okay, Nobel. For this situation, for Nash equilibrium, he had proved Nash. He is died already, and unfortunately, but okay. He proved that there is always Nash equilibrium in a mixed strategies. One kind of mixed strategies. Mixed strategies means that we allow agents not to just choose one strategy, or we can give, well, there's they can choose strategies with some probability. For example, we allow agents to flip a coin and to choose. For example, he can say that the first agent that probability or that his action will be S1 is, for example, 0.5 and as 0.5. We allow this such kind of strategies, so it's probabilities. And now, in this case, the strategy of an agent, it is not just choosing one thing, but it's in fact it's a distribution, a probability distribution, and we can have here the very famous theorem that there is always equilibrium here in such in such a game. Okay, wait a minute. Oh yeah, sorry. Yeah, we can. I think we can have a break from now, so it's 11 o'clock till 11:15. Is it okay? Wait a minute, I will check this discussion. I cannot see messages right now. Wait a minute. No, still cannot see. Okay. Okay, 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 okay. Then we can make a pause here and stop, make a break, and continue in 15 minutes. Okay, now it's 11, 15, and we can continue. Go on. So I have described the Nash equilibrium in some kind of pure strategies when an agent is not allowed to use a probability distribution to choose strategies, and mixed strategy. Mixed strategy. For example, we don't know where our competitors will go, to the first customer or to the second customer. We know only a probability distribution, or we can predict the probability distribution, and we can try to calculate such mixed equilibrium. Okay, it's Nash equilibrium, but it's not the only way how we can think about equilibriums. And so the first good idea is that good news that we have always equilibrium in the mixed strategies, but problems are a coordination one. How can we predict the actions of agents if there are several Nash equilibriums, 3, 4, 5? How should we imagine that agents can choose between them? It's a problem of coordination game. Another thing is that Nash equilibrium can be very complicated, and it's very difficult to imagine the agent who can give, accurately calculate this equilibrium. For example, we don't expect from um, a car driver that he can solve some differential equations or something else. Sometimes we should because he has software, but it's not obvious. Why should he have it? Okay, this problem, cooperative thing, is also a very strong assumption that there is no a cooperative interaction between agents. But it's very important, this equilibrium, and we will use it in our problems there. It's not the only way to talk about games or to talk about actions of other people just using games in a normal form game. For example, chess or other games are not in this form. So it's extended form. So when there is a state like A, and then agent have to choose between variant alpha and beta, and then another agent has to choose, and so on, like in chess. It's another way, and there is an and if information is perfect here, I mean everyone knows the rules and so on. So there is a theorem there that every such game can be written in a normal form game. Unfortunately, this way can be very, very complicated. We have to list many opportunities, and the set of all strategies in this form will be very large usually. That's why people usually don't want to write down these games in extended form into the normal form game. Usually it's not very good idea. But there is a theorem that it is possible. It's not very difficult to show that it is possible. Well, I'm not sure if we have to assume axiom of choice from the theoretical mathematics, but still the assumption is very weak for this. Okay, but it's not enough for us. We do have games here, but we want also add some uncertainties, some probabilities, even not in like probabilities on strategies, but we also want to have some information, what agent 1 knows about agent 2, and so on. In this case, we can add to set of agents, the set of strategies, and set of utility functions, also information strategy or epistemic model structure of the game. We can use it to model such situation. What is the problem here? We can imagine that, for example, we don't know if this customer is available right now. So we want to get them some product, but we don't know if his time window is open right now, or maybe it's closed. So is it available for this delivery, or maybe he's not available. So we can say that that A equals theta equals false if delivery is not available, theta is true if deliverable, if delivery is available for this customer. And we have several agents. So let the customer is available. So the real value is true, but the first agent, he can believe he can think that it's not true, that this customer is not available, but at the same time he can think that the second agent think that it's true, but the first agent can think that the second agent can think that the third agent think that it is false, and so on. We have a tree here, and it's some kind of epistemic tree, and it's infinite. It's very difficult to handle, but there are many assumptions that they can make it very compact structure and to solve equilibriums and so on. But the problem is then we want to model situation when we have a lot of alternatives, and we want to know what agents think about what other agents think. It's very difficult sometimes. One of such approach is epistemic approach. Which is very similar, which is a part of model logic. There are many models for this, but I will give you the basic idea for the one of the simplest one. So the idea is just that we can list all possible alternatives here. Like, for example, here theta f theta is true. Two possible alternative, and we can connect some of them in such a way that, well, and mark, for example, is agent A. We say that agent A cannot distinguish between this alternative and this alternative. And the same here. And agent B, he cannot distinguish these two alternatives. And for example, these two alternatives cannot be distinguished, but A and B at the same time. We can write down it or describe it in another way. When we say that there is an agent, and we just list all alternatives that he thinks are possible. So it's for agent A. Each alternative can be connected to another agent B. So this alternative is considered possible for agent A and for agent B at the same time, and so on. So this one is some kind of epistemic logic. This one is another structure. Usually, in some cases, they're equivalent. Sometimes they're not. There are special axioms here for these words. Well, for these worlds, yeah, here for these alternatives here. We can say that there are alternatives. List them here. And agents just cannot distinguish them, so they have some kind of partition here. Partition for agent A. And we have such partitions for every agent. It's not a very easy way to think about logistics and applications and so on, but it's very fruitful to formalize the basic idea when we have agents who have to reason about other agents. And usually when we talk about some certain cases that I have mentioned before, we have to have, at least we have to find any assumption about epistemic condition of such model. So what agents think about it. Okay. I will tell about this situation a bit later, but just to connect it to the branch and bound case algorithm. The main idea of this algorithm, we will discuss it later in details, but the main idea is when we have to compare all possible solutions to find an optimal solution, we have to compare them, and it looks like we have to check all alternatives, and there is no way how we can simplify it, simplify the optimization procedure. But we have some ideas how this procedure can be simplified. For example, in some cases, it was used for chess and for other games before machine learning and other techniques, and sometime in combination with it. The idea is that if we found a solution, well, let solution be a vector, just one, and we found here. So we consider this solution, but we don't know what we have here. And we find out that the supremum of our utility function here for different values of the tail is, for example, such, and infimum, the smallest value, this situation. And then when we try to check another one, for example, when we know this part and don't know this part, should we check all these alternatives? It could be that a supremum or largest value, when this one is fixed, here, like this one fixed, is let it be G and infimum. And if in this case the best of this is just less than the worst in this case, then we should not spend time to consider all these variants. We cut off it. Just say that we don't need them if we have such a condition. And that's the main idea. So we can use branches. We can split our possible solutions into several parts, and then try to find supremum and infimum. Sometimes we can do this, and then just cut off the worst variance for this. How can we use this to apply it to the uncertainty and so on? When we do not talk about probabilities, but just interval uncertainty, so when we have several possible variants, we need to assign here an additional parameter. So it's not just our routing, but also an alternative. So our utility function depend not only the routing itself, or our plan to route, but also alternative, for example, alpha 1. So it could be that there is the same routing, but it's another alternative. So our utility function now depend on some uncertain parameter, but we still can do such supremum and infimum operations. So if we found that for any alternative, so the maximum the value that we can get is is less than the worst value that we can get for every alternative for another routing, then we just cut off. So the basic idea is just we use the same supremum and infimum technique, but just consider alternatives. So it's the main idea how we can apply uncertainties to the basic algorithm of branches and bounds for any problem, and especially for traveling salesmen. The problem here is that if uncertainty is very large, so we have maybe almost no idea about what's happening, all possible alternatives is a very big set. So we have many alternatives there, and it's very difficult to compute it, and even to just put into the computer memory. It's a problem there. But in some cases we can do this. So if you have a problem and we have only two parameters, uncertain parameters, we can construct such system and apply branches and bounds algorithm. Okay, this one is okay. So we have checked Sorry, about games. We checked logic a bit. We didn't dive deep in this topic right now, and uncertainty. We also, if we have here a probability, we can just have to handle expectation of such routing, but it's not sometimes very easy task. For example, if we want to find the best routing in this network, if we are given the probability of being out of servers for each street, for every street, then we have to think how to do this. It's not very easy thing. It's possible to do because we can just list it and assign its probabilities and solve using optimization technique, but it's not something that we can call obvious thing. Okay. We have discussed this. How can we use games and other techniques to find equilibrium and other things? Okay, for logistics. The main idea how we can do this is just to list all agents. Okay, we can do this. We can just show routing, possible routing. Okay, we can do this. And then we can assign utility function. Okay, it is possible. And then find an equilibrium there using a net equilibrium criteria and algorithm for this. For example, let we have situation when we have to choose. Well, we have to predict the actions of each agent. So agent from point A have to find the ordering of visiting 2 and 1 points 2 and 1 to get a better profit, well, larger profit here. Okay, it's very easy. So we can just list here. It's like a game theory. So we can say that for agent at point A, there is a variant to go to the point 1 or to the point 2, and then to the point 2, and here to the point 1. And the same we have for the agent at point B. Then we can list payoffs here, as I did before, and apply a Nash equilibrium technique algorithm to find. We will do it maybe later to check how we can use it. Of course, in this case, it's very easy. We even don't need routing in the strong sense. It's just 2 points. We have just to choose between them. But sometimes we can use it for networks to apply it to more complicated cases. Okay. If you have any question, please ask. I will try to answer. Okay. So we move on. Wait a minute. Okay. What do we have here? What kind of problems can we solve here? I have listed before, so let's check the very beginning. Wait a minute. So Bryce paradox is not something that we should just solve. It's paradox. But the technique of Nash equilibrium that I have mentioned before is useful to solve it. So when we have a routing system and we have two alternatives to create a route or do not create, we can check Nash equilibriums for both cases and check uh, utilities for all agents. And so we can find the best solution. So it's a direct way how to check if this routing system, network system, is suitable for our case. When we talk about this problem, when we have to choose how to get from point A to point B, I have shown that it is very tightly connected to the game theory. So this is a payoff matrix. So we have payoffs for each agent. For example, when A find this one and, for example, this one, we can find the output here. And it is very easy to find Nash equilibrium in this certain case. But when we have a network here, it's a bit more a complicated thing. But still, we have an algorithm that we can apply directly. So we just have to list all variants for each agent and then create such table if we have two agents and find Nash equilibrium here. How can we find a solution for this situation? Okay, it's very direct. There is a direct way here, but for large networks, it's not a well, not for big uncertainty. It's not applicable. So just imagine that we have very small network, or we have almost the same knowledge about these roads. For example, we have just like here, only one road, this one, that is known for B, and this road is known for A. And all other roads, all other streets are known for all agents, for A and B at the same time. So for A, it is not known if this street is out of service or no, and for B, this one. And we can list all possible alternatives. There are 4 of them, so we can imagine. So just if we introduce several parameters, for example, let it be SA street here is on service, and SI out of service, and the same for B. B, SP. So on the service and out of service. And then we have 4 variants. So SA, SB, SA, and not SB. Here as not SA, not SB. So not SB means that B knows that this road is out of service. Here. And we can connect them. So A cannot distinguish these two possible alternatives because he knows if this street is on service, but he doesn't know if another street is out or maybe not out of service if the street is on service A. So A cannot distinguish, and here. And for B cannot distinguish these two. This one is a epistemic model for this situation. And the network, this network, can be very complicated. A lot of nodes here. It's no problem. The structure is the same. There are only difference here, just that when A and B will find the solution, they will have to use this large network as a parameter there. But the epistemic structure is very compact thing. It's not an infinite tree because we found a way how to write down it in a compact way. It's an epistemic model. It is very important here to say that we can introduce, and in epistemic logic we usually do this, is an operator like Ka. So it means that that agent A knows that something is the case. For example, knows that road there is on service. And how we can define it. If you have such a model, we can define knowledge is just parameters, or it's just Boolean logical parameters, variables that are true, well, when they have several the same meaning in all possible words. So for example, here is A and here is A. So in every alternative for agent A, this road is on service. So he knows that this road is on service, and so on. Sometimes people use beliefs. We will talk about beliefs later. But it's very important distinction between knowledge and beliefs in these models, that knowledge requires that if somebody knows something, it means that it really so. So if A knows that the street is out of service, this street should be out of service. It has to be out of service, but it must be out of service. But when we talk about beliefs, it is not necessary. So agent can believe that the street is out of service, but it's not obligatory for street to be out of service. It can be on service. So it is belief. We will take later. So here for this situation, green one, we can construct an epistemic model. We will talk how to work with epistemic models, but the basic approach here is just to use a branch and bounds algorithm, but take supremum and infimum, not only for the specific word, but for all alternatives here. Okay. Another thing is when we are talking about probabilities here, for all possible variants, well, it's a difficult thing, but we can try to use some kind of greedy algorithm here. For example, we can assume that, well, we can assign to agent the attitude to risk. So if the agent wants to risk, he will try to use the road with the maybe a less probability of success of service, but with the very small costs. If he doesn't like risk, or he thinks that it's not acceptable, so he maybe prefer the situation with the very small probability of failure, but with the high costs. So we can adjust it, but the uh, main approach here is just to use uh, neutral attitude to the risk. So agent just want to uh, maximize his expected utility. He don't want to avoid risk or take risks. He want just expected utility here. Okay, what can we do in this problem? Here we have uh, a game, and we can, as I have described before, we can list just all actions of agent 1 and for agent B here, and solve Nash, well, and to calculate Nash equilibrium there. And in this case, we can find the solution. If we allow mixed strategies, then we can have always equilibrium. Then we will always have an equilibrium here in mixed strategies, and we can well mesh equilibrium. I think I can tell about one more equilibrium that is sometimes much easier to find. Okay, okay. I have told about this situation, just epistemic models here, and the same when we talk about business processes. So there are different approaches how we can solve this problem and apply it. The first one is just to um, list all choices here, here, and here, and here, all agents, and write a normal form game, very large one, or just to make it very compact. So the main idea is just we try to write down all possible situations and then check the Nash equilibrium property. But it's not a very effective way to find the best solution. Another way is to find best solution here and then at another part, and then trying to combine the best solution here and the best solution on the next step. Sometimes it is possible, sometimes it is not. Um, for example, if we want to make assignment and a shortest path, for example, we have many products, goods, and we want to um, deliver them to the customers. So we need to find the shortest path from each car to the customer and save an assignment problem. And we can easily do this just by splitting into two separate tasks. So at first we have to find the shortest path from each car to each customer, and then we can solve assignment problem. So it's very easy. But sometimes we cannot separate in such an effective way, and maybe we'll talk about this later. Motivation here, well, when we talk about some salary and we talk about employers and other things, it's a very difficult thing sometimes. And how can we use game theory? In this case, uh, solution is very simple. It was found maybe 10 years ago, in the previous century, in 20th century. What is the idea of this? Let us know C and H. Then we want to, well, and let's imagine that we have an optimal plan. So we didn't know, just somebody told us that this value is the best one. Of course, we want to pay to this agent as small amount as we want. So we want just to cover his expenses here. So we want that when agent do what we want, his salary is larger than his expenses. Okay, and we can say that it's just his expenses and very small amount, because we don't want this. Well, we assume that agent would act only if he has some motivation for this. He has non-zero profit. So we cover expenses and give some very small amount. Okay, let it be so, this plan. We still don't know X, but we imagine that this situation is true. In this case, it's easy to write down here this expression. And now we know the salary is just the expenses and some very small amount. And we want to make it as large as we can. So we have a maximization problem, but now we have only one argument. So indeed, this one is just and some epsilon, but we can just do not consider it because it's very small, just maybe $1 or maybe less. Okay, and that's all. So in this case, the solution this one. Unfortunately, this classical situation is not directly applicable to the real cases, and there are some modification of this. The idea is that we cannot force agent to take all risks, because okay, if we pay him, well, and the payment is just here large and 0 everywhere else. But it's not very comfortable for agent, because there are some uncertainties, probabilities, noise, and it's very easy that he can get nothing because just of very small noise here even. So it's some kind of bifurcation point. But in this case, the modification is that it's not such kind of function, but for example, it can be just 2 lines. So we make it smooth to make sure that agent will have something, even if he cannot reach his plan completely. So maybe he has some noise here, so something goes wrong, for example, virus or something else, but he still gets his salary, maybe less, but not so much, and then we have some kind of stable situation. So here we have a solution for this. The problem here is also with the situation when agents, they don't want to share all information with us. For example, the very interesting, and we have time to discuss it now. Let we have several cars or just providers of delivery service. Yes, for simplicity, car one, car two, and we have some money. Oh, I don't know, euros, maybe yens, and we want to give them money to provide this service, and they tell us how much money they need to provide this service for the customers in their cities. For example, here they have C1, C2, but we don't know these costs. Maybe they want to say that it takes more money and time to provide this service. He can say that it's not C1 but C3, C dish that is larger than C1. In this case, we have to spend more money than we should if we know the real situation. So, and it's not a big problem, but if we have very limited resource, we don't have resource that is enough for all these messages. For example, here this provider in Moscow, he wants to have $10 million in St. Petersburg, maybe 20 millions, but we have only 20 for these logistics operations. What should we do? We don't know if it's real numbers or not, but we don't have enough money to give to all of them to provide a service and get profit from this. In this case, there are, and it's a problem. It's definitely applied because we can find it in many cases. It is quantitative because we have special variables here, and it can be applied to logistics as well. It's not essential about logistics. It can be applied to many other areas. But for other case, it is very interesting to check what we can do in this case here. We can imagine a network routing here, a very complicated case, but if we just restrict ourselves by using just 2 points, several points, one of possible ideas for here is a median voter here, but it's maybe later. And we'll talk about this. And another idea here is just to give priority to those providers of service who ask for less money. So we give for this provider 10 million because he asked for less money, and then we give the rest to St. Petersburg provider. It makes them think that they shouldn't give the messages to us too large, because if we don't have such algorithm, the dominant strategy for them is just to ask for all money we have. If we have 20, then Moscow provider should ask us for 20, and St. Petersburg will ask us for 40, and so on. And there is a change between them, and there is no equilibrium there. So they will ask for more and more money, and we will lose here. But with this algorithm and similar algorithm, we can just reduce these risks. Okay. Okay, we have discussed the main problems here. We can, I think that maybe I will add some of them these problems for more detailed research, and I will add some new problems next week. So we have just listed some of them. I would like to introduce the rationalizable procedure of equilibrium. So there is another way how to find equilibrium, not only Nash equilibrium. Nash equilibrium is great, but it's not the only way. What is the other way? We can imagine that we have a table like we did before. So we have strategies for agent 1 and we have strategies for agent 2. It's not necessary to have only 2 agents. We can have 3 agents, 5 agents. It's okay. The method is still the same. Is the table for the profit function, utility function of agent 1, and this one for utility function of agent 2. Agent 1. So the situation is just a point here. So they choose the actions. Okay, what can we do here? As I mentioned before, we can find here Nash equilibrium, but maybe we don't want to solve this problem with coordination and other things. Maybe we don't want. The idea is that we can just, if we believe that our opponent of, if one agent, one player, he believes that his opponent, his opponent is rational, so he believes that his opponent never choose the dominated strategy. What is dominated strategy? If, for example, we see here that all numbers here is larger than all numbers here. So for example, here 5, 7, 2, 1, and here we have 0, 1, 2, and 3. It is easy to see that for agent 1 there is no reason to choose this action here, because whatever agent 2 will choose, agent 1 has more profit, more utility if he change his strategy from this strategy to this one, because it's just strictly larger than this one. This strategy is dominated strategy for this agent, and maybe we should assume, it's very reasonable to assume that such agents, they never choose these strategies. Okay, it looks like very obvious thing, but it launched the process of simplification. What kind of simplification? We can just cut off this strategy here. And maybe in this case, sometimes it is the case, for the second agent, we had 2 vectors like here, and this one is almost dominated by this one, but here at this point this value is greater than this one, so there is no strict domination here. That's why it is reasonable for agent to choose this strategy, and this strategy is also okay. But when we cut off one strategy from agent 1, then this point will be cut off too. And in this case, this strategy becomes dominated, and we can cut it off. and cut it off here, and so on. What will we have? So we will have, as the result of these actions, maybe we have the same, because there is no modification of such kind. But maybe we have such modification, and then we have just a part of this. So only some strategies are reasonable for player A, stay reasonable for player A and player 1 and player 2. Sorry, and here the same. It means that if we are given the large game, we can cut off many strategies, and we have only sometimes very small amount of available strategies. Sometimes it is very useful. We can apply the same method for the mixed strategies. So when we have several vectors, we can cut off those vectors here if it is dominated not only by the single strategy, well, single vector, as I told before, but by mixed sum. For example, we can say that we can cut off some. Sorry, let me have such matrix, and we can list it like O in J, and we can cut off a vector. Vector. So it's I. If there is a combination, so it's U1 is less for, yeah, wait a minute, not here, U E J less than alpha UK J plus U MJ. So we have a combination of strategies, so we can choose probability distribution of two other strategies such that this combination will be better than this strategy, certain strategy. Then this strategy can be cut off. It is computationally not very easy to find such variance, but usually it can be proven in a specific case. The good book for this is epistemic game theory by Anders Peria. Not only him, but he has developed this approach in his great manner. He is in Netherlands, it's Maastricht. He proved some theorems for this, and so on. We also can imagine another thing, another type of equilibrium, the equilibrium of max-min or min-max. So the idea is that agents, they assume that another player will choose the worst strategy for this player. I mean, imagine that my opponent has two strategies. The first one is kamikaze way, to make the very worst variance for me, but it's the worst for him. too. And another variant, maybe not so bad for me and not so bad for him. And I have to choose which one to, which strategy should I use. And maximin strategy means that I also assume that my opponent always is not lead by his own. So his utility function is just the opposite as mine. So he wants to make me suffer as much as he can. In this case, I will choose. I will always assume that my opponent choose the worst strategy for me, and I can try to minimize just my costs in this case. Uh, it's very safe way to think, and it's very safe strategy. So there is no risks. Well, I mean, you are prepared for the worst case, but it's not very applicable for real cases because it is very difficult to think that other players they just want mm, to hurt you, and this is the only motivation for them. It's not usual thing. Usually people they have their own motivation, and it's not a zero-sum game. A zero-sum game means that uh, your utility plus your opponent utility is always zero. So when you win, he lose. So there is no win-win strategies, a win-win situation. But usually there are many such situations. So this maximin way is not applicable here. But some people they use when they want a very safe strategy for this. Okay, so rationalizable way, maximin, and other thing. Okay, Nash equilibrium. Um, I think we have maybe 3 or 13 minutes um, for this lecture. So if you have any question, you can ask me, and I can try to answer to this question. So I have told about uh, exam, homeworks, assignments, and tests, and projects, and so on. So I told about lectures. There will be recording of this. I think that maybe I will send it either in the email via email, or maybe by YouTube with limited access. Maybe it will be a good idea. Or maybe it could be a special place on the Google Disk. So if it is more valuable for you. Okay, okay. I think that since we are at a computer science department, we next week we can try to solve some problem using software. I don't know which one you prefer. I like Haskell, R, Python, and other things. I think Python is the mainstream now for some cases. So I think that we can apply Python for some uh, problems here and compare results. So we can check, for example, traveling greedy algorithm for a traveling salesman person, and add uncertainty, add some games, and I can show you procedures how you can find equilibriums or optimal solutions there in a Python way for some cases. And if you feel that you have some very interesting ideas in this domain that uh, hasn't been covered by me, so maybe you have a very great idea, uh, you can share with us. You can send me and say, Dennis, I have a great model of applied qualitative logistics, and I will be happy if you mention this in your lecture, if you have some knowledge or research in this specific area. Maybe I have, so I can share with you, and it will be profit for you. Okay. 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 So if you have no questions, I can say some just last words, and then we finished today, and we will meet next week. Okay. Okay. I would like to say, okay, I see no questions. So, okay. I see. Will we start in one? Yeah, definitely. Yeah, yeah. I agree that this lecture is very general. I uh, I gave several definitions for this in terms like Nash equilibrium, like mixed strategies, and so on. But next week, we use software and solve just several practical problems. Uh, I we maybe prove some theorems there. Okay, email. Okay, yeah, you can use my email. This one is my email in high school of economics. Or maybe you would like to use another one. This one. I use this one in box to speed up process because I have a lot of messages in high school of economics mailbox, and sometimes it's not very easy to find the right message. I read more carefully the second email. So defidenin inbox.ru. Okay. Okay, consult relevance. Yeah. Okay. So you can use this email to write me some details. Yeah. And considering more details of this topic, yeah, I think that when we just go to the software, maybe some very specific problem, maybe very small, to give you some idea. And I think that it could be a good idea to just maybe approve some theorems if you want. If you have an idea, well, I understand that you have very different experience and knowledge. Maybe you are a great expert in game theory and maybe not so great in optimization, and maybe you are great in optimization but not so great in game theory. So you can adjust the difficulty and tell me that, for example, game theory is okay, yeah, okay. Unfortunately, I'm not sure that I don't have all emails of you. So I will ask manager to provide me with your emails, but I'm not sure that it will be, well, I think that they will provide me with your emails, maybe corporate, like high school of economics.ru or something. But to make sure that I have your email, you can send me just email, and it will make you sure that I have your email. Okay. Yeah, mm, all right. Arrange, yeah, and okay. So I think that now we have discussed all these topics. In some topics on very general level without details, but some of them I think we have discussed in details. For example, high school, for example, Nash equilibriums and some other things. Uh, okay, but thank you for your request. It's very important for me to understand what how to make this course better for you, because sometimes I think that if I give definition, you can read everything on internet, but I should stop myself and to describe something in very detail right here in lecture, to be sure that you know it, and to describe it in a very convenient, a very understandable way, because internet is sometimes not very small place. It's a very large thing, and maybe it's not very good to read it. For example, these books that I have given, they're very complicated, and I definitely will show you some details during the lectures, because it's very difficult to read these books personally. Okay, thank you for your attendance, so that you came here. I'm very proud that I'm having an opportunity to tell you something that I know, and I hope that it will be useful for you. So see you next week at the same time. So at 9:30, and I'm free to answer your questions. Thank you.